graph this one out. We know we're first quadrant. Intercepts, what we had, 75 and 25? So we'll say, what did I write mine as? That doesn't matter. B was first, and G. Okay. Next week. Test on the whole chapter is next week. So we go through, you know that your B-intercept is at 75. Your G-intercept is at 25. And then from there, working inward, so you draw your arrow. The other one, you have intercepts at 31 and 38 and change. Are your two intercepts there? And it was also working inward. Everybody okay on that? So I can. Smartboard isn't the world's greatest thing in the world to use for linear combination because you need to have a little bit more space, but I wanted to make sure I keep it on the board so that way you guys can go back and rewatch this. So now in order to figure out the intercept, where those two guys intercept one another, you can do multiple ways of setting it up, but the easy way to set this one to go is to use substitution from the first equation into the second. It's just a little bit cleaner. There's more than one way to do this, but I thought that was the easiest. So I can say that 5 times 75 minus 3g plus 4g is 155. So 375 minus 11g. All I did there was I did minus 15 plus 4 right away is 155. Moving things around and finishing out, you get g is 20. So you know that g is 20, so that's the second value. Just substitute into the top one, you get 75 minus 3 times 20, you wind up with 15. So you have your bounded region now, 1, 2, 3, of 4 points. 0, 0, 31, 0, 15, 20, and 0, 25 that you substitute back into your constraint. And when you do that, you get, well, this would be 0. You get 40 times 31. Here you get 40 times 15 plus 55 times 20. And then this one you get 55 times 25. And if I'm not mistaken, I do believe the 15 and 20 is what works out to be your maximum value. Okay? Once again, the trick to solving this problem is where those two lines intersect. And when you're trying to find out where two lines intersect, it's solving a system of equations. One suggestion that dawned on me later in the day yesterday is because I know that sometimes you guys get kind of lost at what line is what when you're putting them together. Just label your line if you have to. You say this one was the B plus 3G line. This one was the 5B plus 4G. You know what I mean? Label your lines so you know which ones are intersecting, so it might be easier to go back and figure that out. All right? It's not that you need to, but sometimes you get lost. There's that one. I'm hoping that one was the easier of the three. Now the other two, I'm guessing the last one was easier than the second one, right?
Yeah.
Yes, ma'am. This book was written in how long ago? Yeah, I know that. I know that is. That problem with the corn problem came out of a book that was made 1800s. No, it was probably in the mid-80s. It still has a lot of great word problems in it.
No, it's a really good problem. Like, it works out really well.
Did you get 2 values for maximum?
Yeah.
And that's okay. Because sometimes it does occur with linear combinations. You can have 2 possible maximum values. And that's all right. And you're right. Yes.
My dad was like, oh my god. So he made me write in the real numbers.
Oh, really? How much is corn going for now?
That's
Your dad's awesome.
To plant like an acre of corn, it's about $500.
Not $6?
No. Soybeans about 300.
Mr. Tate, you're a farmer. You'll appreciate this.
What?
I used the Dulciani farmer problem, planting crops for an acre of corn for $6. Miss Butler informed me that her dad said, no, you can't do that for $6. It's how much?
500.
So her dad made her rework the entire problem with the right numbers.
500?
What?
500?
Yeah.
Is that including fuel,
No. This is just rock hogs. Like, this one.
chemicals,
No.
fertilizer?
My dad's organic.
Are we all organic?
Okay, so he was including in their rent?
No, he was not. He was doing the baseline, just the corn itself.
$500 in seed for organic? Wow.
Isn't this awesome? She gets an A for today. Put your name on the fridge for an awesome problem.
Oh, my dad said that too.
Hold it. My dad said the soybeans were this much.
That was awesome. I just thought you'd appreciate that.
Yeah.
That's great. I didn't mean to put you on the spot, but that's really cool. And like I said, that book was really, it's older than Mr. Tame's. It's a good thing I'm going to that bullying thing today. All right. I jest. So, here's what we've got. In the machine one, the machine problem is probably the most complex problem we have seen so far. Would you like to work the corn problem first because it's a little bit cleaner, and then go back to the machine problem?
Yeah, corn. Let's do this in order.
You got stuck on this one? All right. We're already on the board. I know. So let's take a look. So your machine shop is making 2 parts, and they use 3 machines. Part 1 is 4 minutes, blah, 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 and so on and so forth. It makes a profit of $8 on part 1, $5 on part 2. However, the number of units of part number 2 produced must not be less than half the numbers of part 1. There's a weird parameter for us. We haven't seen that yet. Also, each day the machine shop only has X amount of time, so on and so forth. So here's what we've got. You have parts A, B, and C. And what I did when I start to work with a super complex thing, you have parts A, B, machine A, B, and C. Okay? You have machines A, B, and C. I'm going to say part 1 is X, part 2 is Y. Is that okay?
Yeah.
X and Y. X and Y. X and Y. Now, what I'm going to look at right away is that one of the first things that they talked about for all 3 machines, they dealt with time, correct? It's ticking away, moments of adulting. So they're talking about time. In the first, for part A, it has 4 and 5. The next one was 4 and 1. The next one was 5 and 6. I'm just pulling that right out of that paragraph. Are you guys okay with that? Now, we also know that the time cannot exceed specific values. For A, it was what, 120? Now, is that going to be a less than or equal to or greater than or equal to for these cannot exceed time limits? These are all less than or equal to's. Oh, sorry. One was 120, the next one was 72, and then 180. Can I have negative parts? No. So I know that X and Y are greater than 0. I know those 2 parameters have to hold true. Now comes the weird part. It said that part 2 had to be, must not be less than half the numbers of part 1. So that means that part number 2 has to be greater than or equal to half the orders of part 1 is what it's saying, right? So that means that if part 1 is x and part 2 is y, half of the x cannot be less than or equal to the y values. Yeah, because it can't be, must not be less than. Must not be less than means it has to be greater than or equal to. It is a funky statement. All right?
1/2 x can't be less than or equal to y.
Right, because y has to, I'm used to writing y second. That's because y has to be greater than or equal to 1/2 of x. I can write it the other way if you like. Sorry, I just wrote down the fraction part first. Y has to be greater or equal to half of what x is.
I thought you were saying that 1/2 x couldn't be less than y.
No, it's saying part 2 must be, part 2 is the y value. I'm so used to putting x values first, that's why I just did it that way. I just wrote it in terms of symmetry, that's all. Okay. So now I've got, and that's the weirdest one you're ever going to see, in all honesty. You might see something where it's half of what something else has to be. So you've got your, what turns out to be 6 different things that we have to worry about graphing. Okay? Yes, so then we're down to 4. 2/3 of our work, or 1/3 of our work is done. Right? Yes? So now we have a parameter to graph. First quadrant, x's and y's, and I go through my list of intercepts. Now, when you go through your lists of intercepts, we start with our first one. Let's see, we have 4, so we are at 30 and 24 for the first one, okay? Cover and solve, you get 30. Cover and solve, you get 24. 30, 24. And it's working inward. All right, you okay with that? Now, what I'm going to do is change colors so that way we know which ones are which. So B is going to be red, C is going to be purple, and then the other one's going to be blue. Are you okay with that so you guys can see which ones are intersecting where? And I'll make sure you guys remember that one's just the black one. So for the next intercept, I'm at 18 and 72. And also, I know that I'm working inward. And the next one I have 36 and 30. Bless you. So far, so good? All right. Now, the tricky part is how do you graph y is 1/2 x? Yeah, and when you get to one like this, before I try to rough sketch the drawing, what I'm going to do is find those 2 intersection points first, because then I'll be able to tell where it's lying above those points or below those points, because I'm going to have a test point, if you will, of what to check. Let me explain this a little further. You guys see we intersect the red and the black here, correct? So what I'm going to do is figure out the intersection of those 2. It sets up nice and cleanly to use either substitution or subtraction. Do you agree? I'm going to use subtraction for elimination here. So I'm going to say that 4x plus 5y is 120. 4x plus 1y is 72. Subtract everything out. I get 4y is 48. So y is 12. Correct. And by quick substituting back into this one here, I get x is 15. Do you agree? So this point is at the coordinate of 15 and 12. So if you think about y is greater than 1/2 x, is it going to be above that point or below that point? It's going to be below it, isn't it? It's just a quick little way of seeing where is it going to wind up. So we know that the red one was going inward, the purple one was also moving inward. So our last little bit of info here is to figure out that the other one is going to line up. This is tough to draw. Kind of like this. And it matches it here. That's the toughest one to get at. Okay? That's the toughest one to find. Remember, the reason why I'm putting that one in there last, because it's difficult to see how high up or how low it's going to go without actually walking your slopes. And without using graph paper, that's a difficult thing to do. But unless you can plot some point to get a visual reference, then you can kind of get an idea that's going to be below that. All right? So now I just figure out where those 2 points intersect. It's the red and the blue. I know that y is 1/2 x with the red. So what I'm going to do here is say that it's 4x plus 1/2 x is 72. So I take 72 and I divide it by 4.5, and I get x is 18. Therefore, y has to be, I'm sorry, 60. I wrote that. I wrote the wrong line. That way y is 8. That's the trickiest of all these that we have, 16 and 8. So your boundary, since y is greater than that, it's got to be in here. You get this funky little space in here that looks like almost kind of like a trapezoid, but not. It's a quadrilateral. To be honest with you, this is about the upper reaches of where we need to be. If you got everything else plotted okay, except for that 1/2 x, you're doing just fine. All right? We do have a problem tonight that will have something similar to that. Maybe. I don't know if I'm going to do that one or the other one yet. Okay? And then you go through your parameters on that one, and I think you wind up at the 15 and 12 being your maximum. Very good. All right. Let's talk about the last one then. Was anybody close on that one? They weren't. They weren't. And sometimes you can get pretty lucky with some of these things. The farmer. 6 and 12. Yep. All right. This one should have wound up a little bit cleaner for us to set out.
This one's really nice.
Yeah. You're looking to maximize your profit. You know you make 24 bucks profit on corn. Excuse me. Yeah. You've got your $24 of profit for each acre of corn and $48 of profit for each acre of soybeans. Man, that doesn't sound like a lot of money. And you could probably attest to that, right?
Yeah, he was looking at it and he goes, well, profit's about right.
So we're trying to maximize our profit. So we know that it's 24 corn plus 48 beans for our maximize function. We know that we have $6 and $12 for our expenses. And we have no more than $2,400 to spend. So you have 6C and 12B less than or equal to 2,400. And what was the other one we had there? our storage space, you get 12 and 16 for storage.
Wait, Mr. Murphy?
Yes, sir.
How do you get the top, like,
This one here?
yeah, I don't even
When,
know how
when
to
it
get
comes down through all of it, this problem was built into 3 parts. The last part is talking about the maximized part. So this one's worded a little bit differently than some of the other ones. You had to go through the very end of the problem to figure out where you can have to maximize your profits. That's all. Whereas some of the other ones was a little more cut and dry. You want to maximize profits. This one was kind of buried at the very bottom. Like I said, this was just a real old text, so it wasn't formulated as what the newer one was. So we're just trying to use it as an extra example. The rest of the ones that we do from here on out are pretty specific. Let's see here. Was it 12 and 16 less than or equal to 3,600? And then obviously we have to be first quadrant. Excuse me. Now, one thing that I did right away with those two formulas, those two constraints, does anybody recognize that both of them can be simplified right away? 6, 12, 24. I can divide all those out by 6. 12, 16, and 36, I can divide those all out by 4. The reason why I'm doing that, it just makes the numbers a little bit cleaner to work with. Do you have to? No. It's just a little bit easier. All right. So I'm going to simplify them real quick, and I get C 2B less than or equal to 400, and then 3C plus 4B. Because when you simplify it out to find your intercepts, you're going to get the same answers. But when I go to do the intersection points, it's a little bit easier. That's all. So we start with our first quadrant. Corn and beans. 400 and 200. Moving inward. 300 and 225. And then a matter of where those guys intercept one another. The intersection of those, because remember it's moving inward. The intersection of those occurs at when C 400 minus 2B. So we have 3 times 400 minus 2B plus 4B is 900. I'm using substitution.
How did you use that C equals 400 minus 2B?
I move 2B to the other side. Right here, see how I have C by itself and just, I'm going to use setting this up for substitution. I think that it's a little bit easier if you have, whenever you have a variable that's defined by one by itself with nothing else in common, use substitution. So 1200 minus 6B plus 4B is 900. Bring this over, I get 300 is 2B, 150 of beans, which leaves us 150 times 2 is 300. 400 minus 300 is 100. So we have our 4 points to check in our cost. 0, 0. Probably can rule that one out. And when you do this, you get, well, 0, 24 times 300, 24 times 100, plus 48 times 150, and this one is 48 times 150. And one of the things I hope you guys notice is that the last two options, the last two coordinates, give you the exact same value, 9,600. So what happens, depending upon parameters and costs and all that other kind of stuff, it is completely feasible and possible to have a maximum occur at 2 specific locations with linear programming. It is plausible. Does it always happen? No, but it is possible. I think that one's easier than the machine one by far. Are we starting to get a little less fuzzy? Bless you. Slowly but surely less fuzz? No. Well, in our book, oops, wrong one. In our books, once this thinks, on chapter 3, in section 3.4, I know we've done some of the constraint ones. There's a couple of work. Don't put all those papers in your book. You're ready to go. Get a folder. There are 3 word problems that I want you guys to try tonight. Out of your book, on page 167. 21, 22, and 23. 21 and 22 are, I will say this right off the bat, 22 is the easiest. You want to start, it's on 167. Number 22 is the easiest of those 3. I would recommend starting with that. Yeah, I would start with number 22 if I were you, because it's a little bit easier just to get going on it. Correct. After that problem, I recommend going to number 21. On number 21, there is a conversion that you have to do to make the problem work. How many quarts are in a gallon? 4. There are 4 quarts in a gallon. For number 21, you have to know that there are 4 quarts in a gallon. If I can help you on that one. On number 23, you have to deal with a setup with where is it? You have to have 3 times as many jars of tomatoes as salsa. So you have one of those other things where you have 3 times this is more than the other. So you have to remember that little setup there for that one parameter in 23. It's similar in essence to when you set up the rest of the parameters like we did on that machine problem. Plot everything else first before you plot that one diagonal line with the intercept with 0. Okay? Start working on those now. I'll wander around and see how we're doing, but we'll go over these 3, and then I think tomorrow we'll just do a couple more and call it a day on these. Yes, sir? Please, go ahead.
What page is this?
167. I'll write it all down here in a second. Like I say, go in that order. It's a little bit easier. 22 is much, much, much easier than 20. There are other ones. Yeah, I'll put them out there.